Hello everyone, my name is Aniket Das, and in this video I will be presenting our model ColonNet, which won the first prize in Auto-WCEBleedGen Challange V2 hosted by MISAHUB and IEEE. First, let us familiarize ourselves with the problem statement. Gastrointestinal bleeding is a medical disorder characterized by bleeding in the digestive tract. Blood flowing into the GI tract creates a series of problems from short-term hazards to long-term implications. A decrease in blood pressure, a reduction in the amount of oxygen delivered to organs and tissues, and possibly fatal organ failure can result from excessive blood loss from GI bleeding. According to the data provided by WHO, around 300,000 deaths occur worldwide due to GI bleeding annually. Over the past decade, the development of sophisticated diagnostic tools such as wireless capsule endoscopy has improved our knowledge of gastrointestinal bleeding in the GI tract. In one such method, a video of the GI tract trajectory is captured on a belt mounted device during the 8 to 12 hour operation, yielding around 57,000 to 100,000 frames. Currently, it takes a skilled gastroenterologist about 2 to 3 hours to examine a single patient's recorded video frame by frame. This is a laborious task and is prone to human errors. Our solution presents an AI model that aims to assist the doctor and cut short this laborious task for detecting bleeding in WC procedures. Currently, our model is capable of distinguishing between bleeding and non-bleeding frames as well as detecting the bleeding area in the frame and annotating it. The entire model can be broken down into three parts: classification, detection, and segmentation. For classification, we use a pre-trained dense-net model followed by 4 dense layers and a sigmoid layer for binary classification. The detection part uses the same dense-net model followed by 5 dense layers and a final sigmoid layer that gives the maximal and minimal coordinates of the bounding box as the output. For segmentation, our model uses the unit architecture with two convolutional blocks, each for upscaling and downsampling. Now we will discuss about the architecture of our model. It takes a square RGB image of size 224 pixels and branches into a DenseNet 121 layer and unit architecture. The DenseNet 121 branch further gives two separate branches for classification and segmentation, both of which receive an image of size 771024. The classification branch consists of repeated dense layers with ReLU activation, dropout, and max pooling, with a final sigmoid activated layer for classification output. The detection is done by an initial max pooling of pool size 2,2 followed by a sequence of dense layers that use a combination of ReLU and ELU activation. The final layer has a sigmoid activation and gives the coordinates of 2 points of the bounding box as the output. The segmentation task is done by the unit architecture. Our implementation of the unit also uses two paths, a contractive and an expansive path. The left contractive path takes an image of size 224, 224, 3 and passes it through a sequence of double convolution and max pooling layer. Each step in the contracting path halves the image size and increases the number of feature channel. In each step of the expansive path, we have an up convolution that doubles the image size, a concatenation with the corresponding downsampled image, and double convolution block that halves the number of feature channels. The final layer has the 224 by 224 image, which is passed through a final sigmoid layer, which gives us the segmentation mask of the same size. Here is the detailed explanation of the network architecture shown above. In case of medical image analysis, it is essential that we achieve deformation and rotation invariance while being able to provide reliable outputs. Since the number of training images provided were not ample enough, we employed augmentation to increase the size of a training dataset. Horizontal and vertical flip as well as rotation augmentations were used, and all the images were resized to a square image of size 224. For the training of detection branch, images were augmented such that bounding boxes was always present. If the largest bounding box in the image were less than a specific threshold, then more augmented images were generated. The training of our model involved a three-step process in which classification, detection, and segmentation branches were trained separately. The detection branch was trained first with the mean square error as the loss function. Only augmented bleeding images were used for training this branch. This gave us train weights for all the DenseNet 121 layers and the lower branch following it. The next step included freezing these weights and training the classification branch. The training of the pre-trained DenseNet 121 and the detection branch were turned off, and the classification branch was trained. The binary cross entropy was selected as the loss function, and both bleeding and non-bleeding images from the training dataset were utilized. The segmentation branch was trained separately using focal Tversky loss as the loss function and training data with augmentation enabled. Finally, all the branches were combined to create the final model. In all the above training routines, a train validation split of 80-20 was used. The training was done on the P100 GPU provided by Kaggle. Here we have provided the final result of our model. Test dataset 1 contained only 50 images and all of them were bleeding, whereas test dataset 2 included 515 images consisting relatively equal numbers of both bleeding and non-bleeding images. It is to be noted that the type of data in test dataset 1 included images with very small patches of bleeding, and the model was able to classify only about 50% of them accurately, with an IOU score of 0.2029 for the segmentation task. However, test dataset 2, which had more variance in the images, gave better results with an accuracy of 0.8175 and an IOU score of 0.6128. One thing to keep in mind is that if there was no bleeding in the image and our model also predicted no bleeding, then the result was awarded an IOU score of 1. Now we will be looking at few of the predicted results from the validation dataset and test datasets. These are few results from the validation set. And here we have shown few results from the test dataset 1. Finally, these are the results from test dataset 2. From all the above results, we can conclude that our model is well trained. Moving forward to the merits and demerits of our model. Starting with merits, our model achieved 80% accuracy in distinguishing bleeding and non-bleeding images without the need of any image pre-processing. The classification, detection, and segmentation of 515 images took 383 seconds when running on CPU only. The same task was performed in 28 seconds using GPU P100 and 50 seconds using GPU T4. So, an average of 45 minutes will be required for processing 50,000 images on GPU P100. This met our initial goal of processing images at a much efficient rate as compared to a gastroenterologist. Now, coming to the demerits, the model struggles to give good results in images with bubbles and other noise. Pre-processing to remove these artifacts only worsened the situation. Since we do not provide context to the model, it may mistake inner folds or curves of the gastrointestinal tract as bleeding. If the bleeding patches are too small, they could be missed altogether. This can be seen in test dataset 1, where half the images were wrongly classified. Also, if an image contains multiple bleeding locations, the output gives only the bounding box of the largest area. The bubbles and noise resulted in quite a challenge during the training, especially in images where the bleeding was in really small areas. We would require more data of this type to get better accuracy on the above mentioned image types. Now we will discuss the future scope of our model. Now, in order to deploy this model, we suggest returning all the bleeding images along with the 10 preceding and the 10 leading frames, as well as their respective confidence scores, which can be further studied by a doctor for diagnosis. Additionally, our model can be further fine-tuned to get better results. We would like to thank MISAHUB for providing us the necessary data and assistance regarding the challenge. We would also like to thank our Professor Nidhi Kushwaha for her valuable guidance. These are the resources which we used in order to develop and train our model.